Okay, in this lecture we go to chapter 6 of the ISLR book. Linear model selection and regularization. This chapter involves subset selection, shrinkage methods, and dimension reduction methods, consideration in high dimensions. We probably will skip 6.3, but we will speak about everything but 6.3 in this chapter. This chapter is especially important when you have more predictors than observations. And in the real data example that we will see, there are more predictors than observations, and then that can lead to problems, which we learn how to deal with in this chapter. Moreover, the same topics are available in the Elements of Statistical Learning book. Specifically, Chapter 3, Subset Selection, Shrinkage Methods, and 3.8. Here it becomes a little bit too technical. We won't cover the technicalities, but subset selection and shrinkage methods are the two major sub-chapters we'll cover in this lecture and other lectures. Okay. If the number of observations is not much larger than the number of predictors, we have poor predictions. And irrelevant variables also lead to unnecessary complexity. We prefer simple explanations. We prefer parsimony. Okay, that's the whole point. When you find a model, in a way, we find a model that summarizes the data. Simple linear regression. You have a scatter plot, many data points. We summarize that with a line. That's a simple example. Okay. So what are the tools available at our disposal? There are many, but we focus on three: subset selection, shrinkage methods, and a combination of these. Subset selection refers to one of the three categories that we have here. The subset selection approach is about identifying a subset, as it's clear from its name, a subset of the P predictors uh, that we believe are associated with the response. Okay, so we fit a model using least squares on the reduced set of variables. The big question here, though, is how to identify that subset, and yeah, so that's what subset selection does. Best subset selection, whereas okay, that's subset selection. When it comes to shrinkage methods, they fit the model using all the P predictors. However, there is a penalty involved. So instead of reducing the residual sum of squares, we try to minimize the residual sum of squares plus something that is known as penalty. And that penalty leads to the coefficients to be shrunken towards 0 relative to the least square. And shrinkage is also known as regularization. And what it does is it reduces the variance, but it injects some bias. Okay, so we reduce the variance, but we will inject some bias, and sometimes that's good, sometimes that's not good. The amount we want to reduce the variance and the amount that we can tolerate bias is what is it's determined by procedures such as cross-validation. And dimension reduction, this approach involves projecting the P predictors into an m-dimensional subspace, and by computing linear combinations or projections. And this is a little bit technical, so I won't really move into that direction. There are some small issues there too, so let's just ignore that. But let's just focus on best, start one by one, best subset selection. Okay. So what we do is we fit a separate least square regression for each possible combination of the P predictors. Okay, so we can have one predictor, K can be 1, and we fit all the models with one predictor. That means that we go over every single one of the predictors and fit it, and we record the residual sum of squares, and then there's one of the models among these that has the smallest residual sum of squares. Okay? And then we go to 2 predictors and then 3 predictors, and for each of them, let's say K predictors, we fit all the P models that contain exactly K predictors. And how many do we have? We have P choose K models that contain exactly K predictors. We have P choose 2 models that contain exactly 2 predictors. We have P choose 3 models that contain exactly 3 predictors, and so forth. So once we look at all the resulting models, we want to identify the one that is the best. Now the problem is that the total number of possibilities is 2 to the power of P, something we have covered in another lecture. Okay, that's a lot. But let's just start from here. Let's say we had infinite computational power, and if we had infinite computational power, this is what we would do. And then once we have done it, then for each number of K, we have a model that gives us the smallest residual sum of squares or the largest R square, and then we have to perform model selection. M0 has no predictor, M1 has one predictor, MP has P predictor. We know that we know that without even doing it, that always the model with more predictors will have a smaller residual sum of squares. Now, in order to avoid overfitting, we can use cross-validation prediction error, or AIC, or BIC, or adjusted R-square among these P predictors. Okay, so here's an example. Here, what you see is that, so for excuse me. So each of these dots, each of these gray dots, they refer to one of the models with a specific number of predictors. So number of predictors, 1. We have this model, we have this model, this model, and this model. So each of them refers to the residual sum of squares when you fit one of the response to one of the predictors. When you have 2 predictors, these are the corresponding residual sum of squares for each of the models, and then 3 predictors for 2 10 predictors. The red line, the red ones indicate the minimum ones. Among all the models that have one predictor, this is the one which has the lowest residual sum of squares. Among all the models that has 2 predictor, this is the one which has the smallest residual sum of squares, and so on and so forth. And here we see the same thing with R squared. So the figure shows that, as we expect, the quantities, meaning residual sum of square and R square, they improve, they get better as the number of variables increase. And what we see, though, is that after 3 variables, the improvement is negligible, if any. So it becomes a question of whether it's worth having a more complex model with more number of predictors when the same performance can be achieved with 3 variables. Okay. Now the same idea can be applied to other regression models that we do not consider in this class, like logistic regression, etc., etc. And the measure will be not residual sum of square, it would be something called the deviance, but that's not what we are concerned here. So what's the big problem of best subset selection? The big problem is, the big problem is the computational complexity. If P is greater than 20 or 30, suddenly the number of models that we need to consider just becomes extremely large, and it may take a long time, I mean days or weeks, on the laptop to perform best subset selection. So it's not ideal. I mean, it's ideal, but since it's not practical. So best subset selection is this algorithm is rarely used in practice, but this is what we like to get near to it, but we cannot. So we come up with suboptimal strategies, which are computationally feasible, and they work well in practice, more or less. And one of them is forward stepwise selection, which is a computationally efficient alternative to best subset selection. Okay. So forward stepwise, instead of just going over all the 2 to the power of p possible models, begins with a model with no predictor and then adds a predictor, and then one at a time it just adds more predictors until all the predictors are in the model, or as many predictors that can accommodate this fitting are in the model. Okay. So at each step, a variable that gives the greatest additional improvement. An improvement here can be decreasing the residual sum of squares, or increasing the R square, or as we saw in another lecture, the one with the highest, smallest p-value, or add it. Okay. So, and unlike best subset selection, this doesn't involve fitting 2 to the power of p models. Forward stepwise selection involves fitting. There's one model with no predictor, then there are p models with 1 predictors, then there are p minus 1 models with p minus 1 models with 2 predictors. No, sorry. First, we have p options to choose among the variables, right? Once a variable is selected, there are p minus 1 left. Once 2 variables are selected, there are p minus 2 left. So it is just the sum of all the, let me see if we have it here. Okay, here it is. So the number of models that we have to fit here is this. So one null model, the null model, then p minus 1, p minus 2, p minus 3, 2, 0. If you add all these numbers, you get this one, which is quadratic, which scales like p to the power of 2. And this is a significant difference, because this is the way to see it. If we had p predictors and we wanted to do best subset selection, that involves 1 million models. But forward selection with 20 predictors involves 200 models. So this is a significant reduction in the computational resources needed. So forward stepwise selection is known as a greedy method, and the reason is that at any moment we are just adding. We are only thinking what is the best next step. given where we are now, given that we have selected these k predictors, what is the best predictor that we can add? Okay. The problem is that if we make a mistake, or if by mistake we add a predictor in the first stage, then we're just stuck with it till the end. Let's look at an example, a real data example. So the best possible one variable model here is rating, okay? But once we consider other variables, maybe rating becomes unnecessary. And this is what happens here. The best possible one variable model is rating. The best possible two variable model is rating and income. The best possible three variable model is rating, income, involve rating, income, and student status. But when it comes to the best four variable model, it just cards income, student, and limits. Suddenly these four together express something that is more useful than having rating. But when we do forward stepwise, we start with rating, and then we're stuck with it, because then we add income and then steering. So because it's just adding, there's no way to get rid of, and at the very end we end up with rating, income, student, limit. It's okay. It's suboptimal and it works in practice, but we need to be mindful that that is a potential problem. Now, finally, when the number of predictors is larger than the number of observations, we can only have models up to the number of observations we have. That's all. So we still can apply it to scenarios where the number of predictors is larger than the number of observations, but the last most complex model will not have all the predictors. It will have just as many as observations we have. Then we have backward stepwise, and backward stepwise selection starts with the full model. It's the opposite. But like forward stepwise selection, backward stepwise selection is also an efficient alternative to best subset selection. And unlike, it's the total opposite of backward, in the sense that it starts with the full least square model containing all the p predictors, and then it iteratively removes the least useful predictors one at a time. So again, because it removes them one at a time, there is a sense that this is a sort of greedy method. It does not consider, obviously, all the possibilities, and at any moment it greedily only removes the one that improves the performance. And like forward stepwise selection, the backward selection approach only goes through the it's around p square models. So if p is too large, it is a good alternative. Now the problem is that if p is larger than n, then we cannot start with the full model. Okay, so in contrast to forward stepwise, this method can only be a viable method when p is not greater than the sample size. And then there are hybrid methods, and I think the hybrid methods The hybrid methods combine the forward and backward selection, and so that variables are added sequentially, and then after adding, they're also we look at what is the best variable to remove, so that variables that we chose early on but we don't need them now because we have other variables can be removed. So it's a very practical approach and useful, especially in comparison to best subset selection, which requires a lot of computational power. Now, the big question here is, how do we choose the optimal model? Okay, how do we choose the optimal model? Well, there are different approaches. At the end of the day, all of them boil down to some sort of test error. We want a model that performs well on the test data set. And test data set is not the smallest residual sum of square. It's not the largest R square, because these quantities are related to the training error. So there are ways to indirectly estimate the test error by making adjustment to the training error. And those are AIC, BIC, and adjusted R square are such methods. They are based on theoretical assumptions, and they say, okay, if this is a training error and this is the number of predictors we have and this is the noise variance, then maybe the test error is this much larger than the training error. And on the other hand, we can also use try to estimate the test error directly using cross-validation. So these are the various proxies. Imagine that this is the residual sum of square, this is the total sum of square, and these are the proxies. So we have CP, which is Mallow's CP. We have AIC, Akaike information criterion. We have BIC, which is Bayesian information criterion. And we have adjusted R squared. Imagine D is the number of predictors. And what we see is that in all of them, we have something that is related to the training error. This is a residual sum of squares. And then we had this adjustment. And adjusting the training error for the model size available. All of them these adjustments depend on the number of predictors. And the larger the number of predictors, the bigger the adjustment, because the larger the number of predictors, the lower the residual sum of squares will be, and it will be lower, but it will be optimism, okay, because we are using the training data. So to adjust for that, we have a term that is proportional to the number of predictors. And any of these approaches can be used to select among a set of models with different number of variables. So the CP estimate the test mean squared error by this equation. Sigma hat 2 is an estimate of the variance of the error. Okay, and so we use the data to estimate sigma hat square. And essentially CP statistics is just adding a penalty of 2D sigma hat square to the training residual sum square to adjust for the fact that the training error tends to underestimate the test error. If you compare AIC and CP, you see that these two are proportional to each other. There's only this sigma hat square here, which is a constant. In other words, they're proportional to each other. And then we have BIC. The only difference between BIC and AIC is this 2 is replaced with log n. So for any n greater than 7, log n is greater than 2. So BIC statistic generally places a heavier penalty on models with many variables. And hence, BIC leads to a selection of smaller models than AIC. So okay, so BIC tends to give us models with smaller number of predictors. When it comes to estimating the variance in high dimension, this can be very tricky. Sigma hat square, as I said, is an estimate of the variance of the error epsilon. And there are different ways of estimating it. We can use the maximum likelihood estimate, which is just a residual sum of squares divided by how many observations we have. Or we can have an unbiased estimate, which divides the residual sum of squares by n minus d, where d is the number of predictors. Now, when the number of predictors is comparable to n, it's large, then these estimates are very unreliable. Okay, so this is just something to keep in mind. Okay, so here let's look at an example. Actually, let me just speak also a little bit about adjusted R-square. Okay. So as we saw before, as we increase the number of variables, R-square always increases. So to account for that, adjusted R-square has these terms here, which adjust for the number of variables. So a large value of adjusted R-square indicates a model with a small test error. So we want our adjusted R-square to be large. Okay. And the total sum of squares is fixed. N minus 1 is fixed. So finding a model with a large adjusted R-square is equivalent to finding a model which has the small residual sum of squares divided by n minus d minus 1. Okay, so while RSS always decreases as the number of variables increase, RSS divided by n minus d minus 1 may increase or decrease depending on the performance. So, and that's what we see here. As the number of predictors increase, the CP suddenly comes down, and then it slightly increases. So the CP, the minimum CP, which is the minimum AIC, is achieved at 6 number of predictors. When you use BIC, as we said, BIC tends to choose models with a smaller number of predictors. It chooses 4, and adjusted R-square takes 7. So this is just to see that, and let's just look at this and see that these measures will say more or less the same thing, but they will never lead to the exact same result, and that's the uncertainty involved in any statistical modeling approach. Okay. So just to summarize, CP, AIC, BIC, these all have rigorous theoretical justifications. These justifications are beyond the scope of our lectures. They are based on many assumptions, and those assumptions are typically uh, involve very large sample size, n being large. And they are very popular, these methods, but they don't perform well when the number of predictors is um, larger or comparable to the sample size. Okay.